Section 2.4 is going to be our last distinctly different rule. We have not seen this rule at all. After this one, we're going to combine some things and do some other things in the rest of this chapter. But this is really our last derivative rule, and it's called the chain rule. What we haven't been able to do as of yet is what happens when we have sort of functions inside of other functions. So when we were working back in section 2.2, there was a problem that we did, and I know you had one in your homework as well, where it had something squared. You know, you had like a binomial, two terms squared. And what I told you is you have to actually square it out. You have to do all the algebra first, right? And that works just fine if something were just squared. You know, binomial squared, no problem. But algebra is really not nice when those exponents get larger. So if you had been raising it to the power of 4, I don't want to multiply something out 4 times before I do calculus on it. That's not especially friendly. So that's actually where the chain rule comes into play. And not only do I not want to, sometimes I can't. There's not even a way to do something like that. So what you see here is you see a function inside g of x of another function f of x. So there's this sort of a nesting feature, like the nesting dolls at Christmas time and so forth like that, right? They nest inside. And what we're going to do is we're going to take the outside function's derivative with the inside function left unchanged, and then we're going to multiply that by the derivative of the inside function. So we work from the outside in on these. So part of what I'm going to do when we are working our way through there is to remind you to keep asking yourself what's inside and what's outside. What is actually nested here? What are the pieces that I can sort of separate apart and think about them independently? Because none of the rules themselves are changing. It's just changing how we combine them together. So let's take a look at an example. This is one that I was just talking about. When you have something inside of a larger power, really don't want to multiply this out 5 times. Really, really don't. The algebra is awful. But if you'll notice, what you really have here is you have this piece, and I'm purposely sort of blotting it out for the moment. All of that pink piece has a power of 5. And you know how to deal with powers of 5. What do you do? Y'all are wanting to say it. Somebody tell me it. What do? You bring down the 5, and then you make the 5 a 4, right? That's what you do, okay? So that's not going to change. We're going to do that exact same thing. And the part that I've blotted out in pink won't change either. It just stays exactly the same. So I will have the 5 pulled down, multiplied by the 2 because it's already there for a 10. And I'll have a power of 4. And the part that I've highlighted in pink originally, and I just erased, gets rewritten. 6 minus x squared. That's the derivative of the outside, the derivative of the power 5 part. The second part of our product or our chain rule says that I'm now going to multiply by the derivative of what I'd highlighted previously in pink. So now I need to multiply by the derivative of this guy. So what is the derivative of 6 minus x squared? Negative 2x. That's exactly right. So we'll have to be a little bit discerning as we work our way through the next problem. This is f prime. I didn't write mine down yet, so let me write that real quick. Because we do need to clean something up, but I'm still not a fan of us trying to multiply something out 4 times. That is not what it means to clean this up. It simply means to do the algebra that's clean and easy to do, and there is some here. This 10 and this negative 2x have no reason why they cannot be multiplied to give me negative 20x. And then the 6 minus x squared is still raised to the power 4. No reason we can't multiply those, but I have lots of good reasons why we're not going to multiply something out 4 times. right? Yeah. So this is our answer. Let's try another one. This next one doesn't really look like what you might expect the problems to look like here. But it is nested inside of something. It will probably be easier if you think of this as being written like this, though. Right? If you had a single, 1 over x, we did this a minute ago, we can write that as x to the negative 1, right? There's addition and subtraction down there, so I can't pull up each piece individually and write them with a negative exponent. That's not appropriate. But I can bring everything up in a big old, clump and write it as a power negative 1. And the beauty of doing it that way is that if you take a look at that, that looks like something inside of something else. It fits the sort of description of the types of functions we're looking at. So again, this piece right here, the inside piece, and then the negative 1 is the outside piece. So on this one, this is g prime of x, the outside piece, the power negative 1, what will I do with that piece? Pull the negative 1 down in front, and then I will make it a power of what? Negative 2, right? Decrease it by 1. The pink part inside is still the same, so I just rewrite it. X squared plus 3x minus 1. It's super tempting to take the derivative inside there as well. Super tempting. But we don't. We leave the inside the same. We take the derivative on the outside. So what then is the derivative of the pink part, the inside part? 2x plus 3. Okay, so that's the calculus, all the calculus part. The algebra part, to clean it up, number 1, it's what's reasonable, right? And it's also how did the problem begin? Well, if you'll notice, the problem began with this thing that I've changed to be a negative 1 power as a denominator, right? So I'm going to put this all back in the denominator. So I'm going to have x squared plus 3x minus 1 squared, like that. And then the negative in front and the 2x plus 3 can be combined in the numerator. What would that look like? Yeah, negative 2x minus 3. Just distribute it. Okay. So far, so good? Okay, the next problem has 2 distinctly different ways of doing it. I'd like to show you, it's based on how you think about rewriting it. So I'd like to show you the 2 different ways that could be rewritten, and then how each of them would look if you approached it from that perspective. They're both right, they just look different. So one way to rewrite this is to think about everything inside being raised to what power? 1/2, yeah. So this is one way to think about this particular problem. I just take the square root and I write all of it instead to a power 1/2. This feels a lot like the way that we've been doing the last problems. I've got all this stuff raised to a power and I can deal with it in much the same way. The part that makes it less friendly is that the part when I take the derivative of the inside, I actually have a quotient rule to use, right? Because the inside's a quotient. The other way that we could rewrite this and think about it is you could think about each of the pieces individually having a power 1/2. Obviously, it's the same value that I just had. I mean, right, it's not any different. But if we think about it from this perspective, the overarching rule is actually that we have a quotient rule. And within each quotient rule, there's a chain rule. So on our first way, we have a chain rule with a quotient rule inside. On the second way, we have a quotient rule with a chain rule inside each piece. That's the way it works. So I'd like to show you sort of how the calculus works a little bit differently. We get the same answer, but just so that you can see sort of the differences in how you think about it. If you were to ask me which one I would do the first one. That's how I think about this particular problem. That's how I see it. But the other way is certainly fine. There's nothing wrong with it that direction too. So let's take a look at what happens on this first one. So as we mentioned, we're going to bring the 1/2 down, and we're going to decrease the power. So what will the 1/2 power now become? -1/2. Yeah? 1/2 minus 1. The inside gets rewritten, no change, so 3t squared minus 2 over 2t plus 3. All right, now I need the derivative of the inside, which is a quotient. So at this point, I'm taking the derivative of all of this piece. Okay, quotient rule says I rewrite the denominator, so that's 2t plus 3, and I multiply it by the derivative of the numerator. So what's the derivative of this numerator? (6t), that's right. Minus, and I need my numerator now, which is 3t squared. I don't have enough space. Try that again. We'll get to that eventually, I promise. 3t squared minus 2 times the derivative of the denominator. So what's the derivative of the denominator? It'd be a 2, right? All over the denominator squared. Here's the thing. That's messy. Oh, man, a killer. I mean, like really messy. And we can clean some of it up. Not everything is going to be beautiful in the end, but it will be a whole lot better. One of the things that you probably recognize is that I do still have a negative power, right? That -1/2. So that -1/2 will flip my fraction upside down, and I'll make it a positive 1/2. So I'm going to start there. I've got a 1/2 here, and I'm going to flip my fraction upside down, so 2t plus 3 over 3t squared minus 2. And it's all to the power 1/2. I'm going to write each of them to the power 1/2 individually, but it's the same thing. Okay, I flipped my fraction, which made the 1/2 become positive, negative to positive. And then I put the 1/2 on each of the numerator and denominator separately. What's cleaning up over here? Ooh, we've got a lot more cleaning up going on. So this is 6t squared, or sorry, 6t times 2t from 12t squared plus 18t. And then I have minus 3 times 2 would be 6t squared, and then plus 4. All over 2t plus 3 squared. Do you notice that these two are the same? The factor itself, they're both 2t plus 3's, right? You've got a half of a factor on top, and you've got 2 of the factor on bottom. And so it's like having, if I simplify or think about it differently, it's like having x to the 1/2 over x squared, right? Properties of exponents say you can subtract those exponents. If I subtract 1/2, I'll just write it out for the sake of having done it, but 1/2 minus 2, what do I get? Yeah, I get negative 1 1/2 or negative 3/2, which is the same thing as having x to the 3/2 on bottom. Basically what's happening is that 1/2 here is canceling with 1/2 of the 2 down below. So we can clean that part up in ours as well. We still have this 1/2 in front. We still have the denominator of 3t minus 2 to the 1/2. But now we have 2t plus 3 to the 3/2. And that took care of the 2 pink pieces. There's a little more to clean up. We're doing pretty good. This piece right here, I have a 12t squared and a 6t squared, so that's actually going to give me 6t squared. And then we have plus 18t plus 4. And because this 2 down here has a 2 in each of these, we can simplify that as well, right? Cancel out a power of 2, not a power, a factor of 2. So I get 3t squared plus 9t plus 2 over 3t minus 2 to the 1/2 and 2t plus 3 to the 3/2. I told you it was still going to be messy, right? Oh, what's that?
I missed what happened to the 12t squared and the 6t squared.
Say that again.
I missed how the 12t squared and the 6t squared.
There's a 12t squared and a negative 6t squared here. So they added, yeah. Good question. There's a lot going on in this problem. Easy to lose lots of pieces. Okay, any other questions on that horribly messy one? So we're going to do it again, but we're going to do it in a different way now. What's that?
Is that a positive 12 and negative 6?
Yes. We have a positive 12 from here, 2t and 6t, to give me 12t squared.
Never mind, I'm looking wrong.
Okay, that's all right. You're good with it now?
Yeah.
Okay, cool. All right, it's messy, right? Yeah, it is. All right, so let's try it the other direction just so that you can see how it would work. What I'm going to do is I'm going to, does everybody have this one written down? We're all good? Okay, give me just a second. I'm going to make this smaller so that we have screen space without making it go away entirely. Okay, let's give this a go. So I don't have this one written down in my notes, so you're going to have to make sure that I don't make mistakes. You guys can do that for me, right? Absolutely. All right, so we're taking a derivative, but we're taking the derivative as a product rule, or as a quotient rule first. So I'm going to write the denominator down, 2t plus 3 to the 1/2. And then I need the derivative of the numerator. So the derivative of the numerator is 1/2, and then 3t minus 2 to the negative 1/2. And then do you notice how that there's something inside here that has a derivative as well? What's the derivative of 3t minus 2? 3. So that's the chain rule part that's playing out on that piece. The derivative of the power of the 1/2 and then the derivative of the inside. Okay, so that's half of my numerator. I'm already out of space. That's not good. What shall I do? How about this? I have an idea. All right, there's more space. And then I've got subtraction. And I need, yes, Eric.
Inside the 3t minus 2, shouldn't that be 3t squared minus 2?
Did I miss a squared? I may have missed a squared when I was writing it down. Yes, I did. So it wouldn't be 3 at the end, then would it be? It'll be 6t. See, that's what I need you to do. Very well done. I lose things. Okay. Now we need the numerator rewritten, so that's the 3t squared minus 2 to the 1/2. And I need the derivative of the denominator. So the derivative of the denominator, again, has a 1/2. And then I can rewrite the piece in the middle, 2t plus 3 to the negative 1/2. And then what's the derivative of 2t plus 3? 2. Awesome. Now here's the cool thing. I mean, like that numerator is horrid. I mean, we're going to have a lot to clean up there. But what happens when I square the denominator? It's going to cancel out with 1/2, isn't it? The denominator is like as beautiful as it comes. It's 2t minus 3. Wow. At least something worked out nicely on the problem when we were doing the derivative. That part's nice. The rest of it's awful, though, right? Yeah. Yeah, Eric. What's that? Better? Thank you. Cool. Okay, let's see. We can clean up a little bit of pieces here and there as we go. This 1/2 and this 6t can easily simplify, right? The other thing is that if you want to rewrite things with square roots instead, you could do that. I don't think I did on the other problem, so I'll leave them off for now. The 1/2 and the 6t would become 3t. And then the fact is that this being with a power of negative 1/2 right here means that within the numerator, I now have a denominator that's 3t squared minus 2 to the 1/2. It'll be okay. I promise. It's all going to be okay. But that's what I have for now. And then I have much the same thing going on over here. Here's that 1/2 and that 2. Those actually reduce to 1. I have still minus the 3t squared minus 2 to the 1/2. And on the other half, then, I have this as a denominator, or I'll write it as multiplication for now. And it's 2t plus 3 to the 1/2. All over 2t plus 3. Are all my pieces there? Okay. Good news, good news. Let's see. Oh my goodness, there's so much going on. What do I want to do? Let's rewrite. Oh no, I don't know if I want to do that. So it was such a good idea when I first started, and now we've got such a mess to deal with. All right, let's get common denominators within the numerator. The 2t plus 3 in the denominator, we'll have to clean that up in a minute. But we can get common denominators within the numerator. So the denominators, of course, don't match at all, right? 3t squared minus 2 and 2t plus 3. So we're going to multiply them, by each other. So I'm going to have this 2t plus 3 to the 1/2 is still in the numerator. And I'm going to multiply by another 2t plus 3 to the 1/2 so that it will have it in the denominator now as well. And I still have my 3t. All over the same 3t squared minus 2 to the 1/2. And then that 2t plus 3 to the 1/2 that I already had. That's what I did. I put those in and they weren't there before. Are we all good with that? They weren't there before. Sorry. Okay, and then the other piece right here will still be here. So that's 3t squared minus 2 to the 1/2, which is what I'm multiplying the numerator and denominator by on this piece. 3t squared minus 2 to the 1/2. And then you can see the original denominator, is there from before, right? And then the numerator is now being multiplied by the original piece, or the other piece that wasn't there too. So they're all there now. Common denominators are there. And all of this is over 2t plus 3. And since I have a single fraction on top now with another denominator, the denominators can be combined to be together. And let me show you why. I don't want you to just take my word for it because that sounds like a funny statement to make. But basically, here's what I have is all of this stuff over 2t plus 3, right? And if I multiply by the reciprocal, 1 over 2t plus 3 and 1 over 2t plus 3, do you see how the secondary denominator here would cancel itself out? And that 2t plus 3 would now be in my denominator? Yeah, that's what happens. And so I actually don't have a double denominator anymore. So I'm going to clean, actually, no, let me leave it there. Might as well. So my denominator now has 3t squared minus 2 to the 1/2 and 2t plus 3. And I have 1/2. And I have this one, which has a power of 1, so that's 1 1/2 or 3/2. And we're getting really close to the end of the problem. Really, really close. Because lovely things are about to happen. What happens when I multiply out 2t plus 3 times 2 to the 1/2 times 2t plus 3 to the 1/2? Yeah, they have a power of 1, right? So that's 2t plus 3 times the 3t that's already there. So I have now 2t plus 3 times the 3 that's beside it. Sorry, 3t. Minus. And over here, I have 3t squared minus 2 to the 1/2 times 3t squared minus 2, which would be 3t squared minus 2 to the 1. So, 3t squared minus 2. If I simplify and clean it up, I have 2t times 3t, that would be 6t squared, minus the 3t squared gives me 3t squared. And then I have 3 times the 3t, that's going to give me 9t, so plus 9t. And then I have minus the negative 2 for a positive 2. And the denominator is the same. I'm going to hold my breath as we take a look back. Is that what we had on the previous problem, the way we worked it out? It is. Oh, good. Oh, good. So first thing I hope that you recognize is that they're both awful, right? But what I'd really like for you to take away from it is that either way gives you the same answer. There are two distinctly different ways of doing this problem, and when they clean up, as you continue to clean them up, they will clean up to the same value at the end. All right, let's do something so much easier. Are you ready? Way, way, way easier. I know you're all bearing with me through the messy one. This is way easier. All right, the derivative of y equals sine of pi x. This one actually doesn't even look like it has something inside of something else. My suggestion to you always is to ask yourself, if I were putting this into my calculator, where would my calculator force me to put parentheses? And then to actually put them there. So where would your calculator force you to put parentheses if you were entering this into y equals? After the sign? Like that? And then at the end, right? That's exactly what it would do. Your calculator would force that to happen. And that's good because the calculator would want to make sure that it understands that all of that's what's inside of sine, not just the pi, right? Yeah, because it would make a difference. So because I have parentheses now, it's a lot easier to identify what is inside of something else. The part that's in the parentheses is the inside. It's the pink piece that I keep highlighting as I'm working. All right? So the outside function here doesn't look like a power. All the other problems I've done, the outside function looked like a power. This one doesn't. This outside function looks like sine. And that's okay. We can still do the problem, no problem. What is the derivative of sine? Cosine. And the pink piece gets rewritten, pi x. And then we take the derivative of the inside function, the pink part. What is the derivative of pi x? Just pi. Remember, pi is just a number. I know it's not like 1 through 9 or something like that, but it is just a number, all right? Pi. And then the only thing to do to rewrite that, just in terms of like cleanliness, so to speak, is to put the pi at the beginning. You can put the parentheses still around the pi x if you want to leave them off, because the original problem did, that'll be fine. But this is your derivative. Can everybody say hallelujah, that was easier? Hallelujah, it was definitely easier. The next one is as well. I don't think any of them are as bad as number 3 was, so that's good news. All right. This is an interesting one, though. Again, where would your calculator force you to put parentheses and things like that? So if you were putting this into your calculator, how would it have to look? You'd put it at 5, yep. And then what? And then what was that, Eric? Cosine and then the parentheses of 3t, like this? Yep. Really close. It would also need you to put a set of parentheses. I'll use parentheses like that. Yeah. So there's actually 2 sets of parentheses on this one that you would need to actually use for your calculator to understand what's happening. The angle inside is 3t. The cosine of the angle, all of that's what's being squared. And this is how you'd have to put it in for your calculator to understand what's really happening. But that's kind of cool, because what you notice now is that there are actually 2 inside functions, right? One inside function, I've decided I should use blue, is the 3t. Okay, definitely inside of a set of parentheses. But we have another inside function that's all of this, highlighted in peach. That's actually the color I chose, peach. So, the squaring on the outside is an outside function that we will start with. So our first step will be to take that 2 and to do what with it? Bring it down to the 5 so that I get a 10 at the front. And everything gets rewritten to the power 1, which is not a very exciting power, but that's okay. Not exciting means less mess, right? It really does. All right, now I want you to focus on everything that was in pink. Peach. Cosine. Not the blue part in the middle, not the 3t, but the cosine part. What's the derivative of cosine? Yeah, negative sine. And the blue part stays the same. 3t. Okay, so I'm working outside in. I started with the power 2. And then I dealt with the cosine. These are nesting, right? And now I'm going to deal with the 3t. So what's the derivative of 3t? 3. This problem is nice in the fact that the power 2 became a power of 1, so I don't have any powers left. That's actually fairly friendly. I can clean some things up too. The 3 here in this 10, for example. That's 30. The negative in front of sine, that's going to make that a negative 30. And now I have cosine of 3t, parentheses if you want or not, times the sine of 3t. Sine 3t, cosine 3t, that's actually another trig identity too. We don't focus too much on all of the there's tons of trig identities. We're not trying to get lost inside of the world trig, okay? So we're good at this point. We're good. Pythagorean identity is kind of the only one that crops up that requires simplification. This is just so doggone nice. All right? All right, one more with the same directions, which are to simply find derivatives. Y equals 3x minus 5 cosine of pi x squared. Alrighty, so what do we have going on here? Well, 3x is nice. What's the derivative of 3x? 3. You betcha. What else? Well, I have a 2 here. And I have a parenthesis here. So I think the problem looks a lot like my last problem, doesn't it? I already see one of the sets of parentheses. The other one that's sort of not written in, but that's there, is right here. So what are we going to do? Well, again, working from the outside in, we start with the power 2. It's the furthest thing out on this one. So the 2 will come down, right? Negative 10. And I rewrite to the power 1. Okay, so I've dealt with the power 2. Now I'm moving in, and I'm going to deal with the cosine next. What's the derivative of cosine? Negative sine. Again, of pi x. I rewrite the next piece. And working my way in one more time. What's the derivative of, oh, this is why I screwed this up. Okay, erase it, start over. This is what happens when you're not paying attention to your notes. I was trying to show you the difference, and then I totally screwed it up. The previous problem had the 2 here, correct? Yeah. This is actually telling us that this piece is only things squared. I'm so sorry. So because it didn't have those functions, those parentheses there that I tried to put in there, it's not telling us that the cosine is squared. If it wanted cosine to be squared, it would have put the square here, and it didn't. So what's actually being squared is this piece right here. That's actually a lot easier of a problem, because really what I have here then is pi squared x squared. That's what the function inside is. I only have one inside function. It's this piece. This is my inside function. So again, let's try this again. So sorry. There's a 5 here at the beginning. What's the derivative of cosine? Because it's the outside function now. Negative sine. The inside stays the same, which is pi squared x squared. And then we need the derivative of the inside, which is the pi squared x squared. Well, although you may not like it, pi squared is just a number, right? So it's just pi squared. But what's the derivative of the x squared? 2x. Like that. Okay, so cleaning this up, we have the 3 at the beginning. This negative and this negative make it a positive. So positive 5. Whoops. Let's not put the 5 yet. The 5 can be multiplied by all of this, right? Pi squared 2x, so that would be 10 pi squared x. And then I have sine of pi squared x squared. It's also not the only way to do that problem, but it works pretty well. Emma, there was a mistake that was made while you left, so make sure to watch this one again, because I did something wrong, but we fixed it, okay? Any questions on that one? All right.